Hello, Dr. Moya here, and I'm trying something new. This is Pale Blue Pod at night, a time for all the friends of the universe to wind down and get cozy before heading to sleep. No laughs, no games, no excitement, just calm. On Pale Blue Pod at night, I'm going to read from a book or a paper as slowly and soothingly as I can. I wanted to start with something I know I have the copyrights to, something you won't have read before, something so boring it's sure to put you right to sleep. I will be reading from my PhD dissertation, so feel free to lie down, close your eyes, and let the words pass in one ear and out the other as you listen to Why Are We Here? Constraining the Milky Way's Galactic Habitable Zone by Moya Adar Scanlon McTeer. Submitted in partial fulfillment of the requirements for the degree of Doctor of Philosophy under the Executive Committee of the Graduate School of Arts and Sciences at Columbia University in the year 2021. Abstract. Our solar system is just one of billions in the Milky Way, situated about halfway from the galaxy's core to its edge, and nestled safely between a pair of spiral arms. Out of those billions of planets, ours is the only one that we know supports life. This begs two questions. First, is our location in the galaxy especially suitable for life? Second, if we want to find other life out there, where should we focus our search? In this dissertation, I contribute answers to both questions by seeking to better understand the boundaries of the Milky Way's galactic habitable zone, or the place in the galaxy where habitable worlds are most likely to be found. We start in Chapter 2 by introducing a novel method for finding the average height of surface features on exoplanets, a characteristic that influences a planet's habitability but was heretofore unknowable. We use elevation data for the rocky bodies in our solar system to simulate their transits in front of stars of different sizes. We provide a relationship between the scatter at the bottom of the resulting light curves and the so-called bumpiness of the transiting planet. In Chapter 3, we zoom out from planets to get a better understanding of the dynamical and chemical evolution of the Milky Way, which are both crucial for constraining the galaxy's galactic habitable zone. We use the extreme deconvolution Gaussian mixture model to identify overdensities of stars in both velocity and action space, called moving groups or orbit groups, respectively. Velocities and actions are calculated using data from the early third data release of the Gaia mission. When we analyze the chemical abundance distributions of these moving and orbit groups with Galah DR3 data, we find that using velocities alone to define moving groups, or even using velocities and actions together, yields an incomplete view of the underlying density distributions and their origins. Our chemical analysis also confirms expected chemical evolution trends in the solar neighborhood. Next, we explore the effects of stellar motion and galactic dynamics on the habitability of planets in different regions of the galaxy. In Chapter 4, we use Gaia DR2 data to calculate three-dimensional galactocentric velocities for stars observed by the Kepler spacecraft. We compare the velocities of confirmed Kepler host stars to those of their non-host stellar twins, and we find that there is no relationship between stellar velocity and planet occurrence in the solar neighborhood. In Chapter 5, we shift our attention to the Milky Way bulge, where stars are closer together and moving more quickly on more elliptical orbits than in the disk. We simulate the orbits of bulge stars and use a semi-analytical method to derive the rate of close stellar encounters. We find that roughly 8 in 10 bulge stars will come within 1,000 astronomical units of at least one other star every billion years. Half of these stars experience dozens of these encounters every billion years. These encounters have dramatic consequences for planets, and our findings strongly suggest that the Milky Way bulge is not the most suitable environment for life. In Chapter 6, I share an overview of the science communication and outreach work I've done while in graduate school, and explain how it's so closely tied to my research on galactic habitable zones. Chapter 1: Introduction and Background. Once upon a time, 4 scholars, a philosopher, a geologist, a biologist, and an astrophysicist, gathered to discuss the meaning and origin of life. "Why are we here?" asked the philosopher, by which she meant, "What's our purpose?" Following in the millennia-old footsteps of the deep thinkers who came before her, she wanted to know what we are meant to do with the lives we are given. "Why are we here?" countered the geologist, who knew better than most how much our planet has changed over the last 4.5 billion years. She was struck by the seeming improbability that we would find ourselves here to ask this question now, at this point in the planet's long history. "Why are we here?" responded the biologist. They had spent their career studying human evolution, trying to make sense of the millions of factors and events that had to line up just right in order for them to even have this conversation in the first place. "You are not thinking big enough," said the astrophysicist. "The real question is, why are we here? There are more than 100 billion stars in the Milky Way galaxy, a 13 billion-year-old galaxy with a disk about 30 kiloparsecs wide. In all that time, across all that space, we find ourselves orbiting one average-sized star about halfway between the galaxy's center and its edge. Is there something special about our place in the Milky Way that makes it suitable for life? Are we in a particularly habitable part of the galaxy, or is our presence here merely a coincidence? That is what the astrophysicist wants to know, and she's right. It's a big question. This dissertation is her attempt to add to the answer. Chapter 1.1, Motivation. Astronomers' interest in the concept of habitability started with the other planets and natural satellites in the solar system. I call this the planetary scale of habitability, the smallest scale where factors like internal heating, surface gravity, and atmospheric composition are taken into account. After exhausting the list of worlds they could directly observe, the astronomy community turned their attention to thinking about habitability on the stellar system scale. This led to the definition of the circumstellar habitable zone, also known as the Goldilocks zone, or the region around a star where the temperatures are just right for an orbiting planet to have liquid water. The important factors to consider at this scale are the host star's luminosity, a planet's orbital radius, and its orbital eccentricity, though a planet's intrinsic characteristics still play a key role in determining habitability. Due to historic, technical, and methodological limitations that made it nearly impossible to observe a planet's intrinsic characteristics, much of the search for habitable worlds has focused on this stellar system scale of habitability. The concept of the circumstellar habitable zone, along with the strides made to understand planet formation in the 1970s and 1980s, reveals one very important adage: know thy star, know thy planet. A planet's traits depend on its host star, and we know that stellar populations vary throughout the galaxy. It follows that there might be some galactic characteristics that influence the genesis and survival of life. A handful of astronomers turned their attention to this third galactic scale of habitability before the first exoplanet had ever been confirmed. We now know, thanks to the confirmed discoveries of more than 4,000 exoplanets, that planets are quite common in our galaxy. Exciting though that may be, it does complicate the search for extraterrestrial life. Therefore, this third and largest habitability scale might be more important now than ever before, because constraining the Milky Way's galactic habitable zone can make the search for extraterrestrial life more efficient. Section 1.2 Past Attempts to Constrain the Galactic Habitable Zone. Though there were some relevant studies in the last few decades of the 20th century, the definition of the galactic habitable zone was first formalized in a peer-reviewed scientific paper as the, quote, region in the Milky Way where an Earth-like planet can retain liquid water on its surface and provide a long-term habitat for animal-like aerobic life, end quote. Gonzalez et al., 2001, estimated that the Milky Way's galactic habitable zone is an annular region in the thin disk, approximately centered on the Sun's position at 8 kiloparsecs from the galactic center. I personally prefer a less Earth and human-centric definition of the galactic habitable zone, the place in a galaxy where life might be most likely to thrive. But I can also appreciate that a more limited definition can further optimize our search for extraterrestrial life. Galactic habitable zones are determined using a set of 3 criteria based on our undoubtedly limited human understanding of what life is and needs. Number 1. Life needs metals. As far as we know, terrestrial planets and complex life forms both require an abundance of elements heavier than helium. Number 2. Life needs to be free of harmful radiation. Supernovae, gamma ray bursts, and ionizing radiation from young and massive stars can all prove to be dangerous for life. Number 3. Life needs time. Stellar evolution, dynamical effects, and gravitational interactions can all render a once habitable world inhospitable for life. Since 2001, the Galactic Habitable Zone research field has gained traction amongst astronomers. Their work can broadly be divided into 4 categories, each one a different lens through which to view the Galactic Habitable Zone problem. They are chemistry, radiation, time, and dynamics. In the following sections, we examine each separately, except for time, which is inextricably accounted for in other studies that consider any kind of time evolution. Section 1.2.1 Chemistry. In their field-defining paper, Gonzalez et al., 2001, posited that metallicity is likely the, quote, single most important factor, end quote, in determining how habitable a particular galactic environment is. The outer edge of the galactic habitable zone, they claimed, was set by the declining metallicity gradient in the Milky Way disk. The inner edge is set by radiation limits from dense stellar environments and supernova explosions, which we will discuss more in section 1.2.2. More specifically, they were interested in the chemical evolution and distributions of silicon, magnesium, and iron, which were hypothesized to influence the mass of a terrestrial planet's core relative to the mass of its mantle. They also say that the radioactive isotopes uranium-235 and 238, thorium-232, and potassium-40 are necessary for maintaining favorable surface temperatures through radioactive decay in the planet's interior. But they don't provide exact acceptable ranges or values for those abundances, except to say that they should be similar to Earth's. Johnson and Lee, 2012, provided an estimate of the minimum iron to hydrogen abundance ratio for forming terrestrial planets according to the core accretion model. Planet formation is essentially a race between two processes: dust grains settling onto the protoplanetary disk and coalescing into planets, and photoevaporation of disk molecules by the host star's radiation. In metal-rich planetary disks, dust grains settle and coalesce more quickly, and photoevaporation happens more slowly because the heavier grains are harder to evaporate away. By comparing these timescales, Johnson and Lee, 2012, found that the minimum critical iron to hydrogen abundance ratio for terrestrial planet formation is described by an equation, where r is the distance between the would-be planet and its host star. In this relationship, the critical metallicity is lower for planets closer to their star, which is consistent with observations of stellar systems with close-in rocky planets and further out gas planets. Hot Jupiters and the question of planet migration notwithstanding. Interestingly, this relationship only has a weak dependence on the initial size of the dust grains in the protoplanetary disk. Since then, several studies have confirmed that higher metallicity stars are likelier to host more and larger planets than their metal-poor counterparts. Wang and Fisher, 2015, found that this relationship holds for all planets, though it is strongest for gas giants. Souther and McKay, 2012, found that non-planet hosting field stars in the solar neighborhood have iron to hydrogen abundance ratios around -0.2, while planet-hosting stars in the same region have much higher iron to hydrogen abundance ratios, around 0.4. Finding the critical metallicity for rocky planet formation and finding the places in a galaxy with the necessary abundances are two different matters. After the provision of the former, several studies sought to discover the latter through chemical evolution models. Following in Kurigi et al. 2013's footsteps of using chemical evolution models of the galaxy to find the Andromeda Galaxy's galactic habitable zone, Spitoni et al. 2014 included gas radial inflows in their chemical evolution model to find the galactic habitable zone in both the Milky Way and Andromeda. Both studies assume that the formation of habitable terrestrial planets is based on the iron to hydrogen abundance ratio of the environment where the planet and its star formed. Spitoni et al. 2014 found that the primary effect of including gas inflows in their chemical evolution model was to increase the number of so-called habitable planets in the galactic habitable zone by 38% in the Milky Way and 10% in Andromeda. But including inflows does not significantly change the location of the galactic habitable zone. In Spitoni et al. 2017, they repeated their previous study, but considered dust evolution and the occurrence rates of planets around M and FGK stars in their galactic chemical evolution model. They found, unsurprisingly given the relative abundance of M stars, that they are 10 times more likely to host habitable terrestrial worlds than FGK stars. It is worth noting that both Spitoni et al. 2014 and Spitoni et al. 2017 define a habitable system as one with rocky planets, but no gas giants or hot Jupiters, because the latter two planet types can destroy habitable Terran worlds. This is at odds with the obvious example of our own solar system, which has at least one habitable terrestrial planet and multiple gas giants. The literature is mixed on whether gas giants, whose gravitational influence and magnetic fields can shield inner planets from devastating comet and asteroid impacts, but can also redirect such objects toward the inner solar system, where they either result in catastrophic collisions or provide volatile materials necessary for the emergence of life. The literature is mixed on whether these planets are good for habitability. The literature does seem to agree, however, that the Milky Way's chemical distribution and evolution place the galactic habitable zone as an annulus between 7 and 9 kiloparsecs from the galactic center. Interestingly, several studies have attempted to use chemistry to constrain habitability outside of the Milky Way, either by defining the galactic habitable zones of other galaxies, or by trying to determine which types of galaxies are the most habitable. For example, Dayal et al. 2015 found that the number of habitable terrestrial planets in a galaxy increases as galactic stellar mass increases and as star formation rate decreases. To make sense of this, let's turn to radiation as a consideration for galactic habitability. But we will explore section 1.2.2 radiation in the next installment of Pale Blue Pod at Night, which will be available for my patrons at patreon.com/palebluepod. I hope you have the sweetest of dreams and that you remember that the universe is your friend and that you are space. Good night.